Right, so let me first thank the organizers for putting together this wonderful meeting and giving me the opportunity to speak. So I will talk about machine learning and string theory, so how we can use machine learning in string theory. And this is a field that where the first papers emerged some 7 years ago now, I think. So it's becoming more mature as a topic, but there's still a lot of unsolved problems, and there are still a lot of areas of string theory where machine learning tools have not been applied. So what I'll do today is that I'll talk around work that I've done together with the people mentioned here, so Larry Anderson, James Gray, Jakub Hendy, Andrei Lucas, Fabian Rühle, Robin Schneider, and Moritz Wange. The work that I've been doing is in the context of string compactification and deals with geometrical questions related to string theory in that context. But what I want to do is to convey to you that these tools can be applied outside of this field. So in order to do that, I've tried to sort of explain how we think about how to use machine learning tools in this setting. And I'd be very interested to discuss with you after the talk and also during the breaks about problems that you might have, and if you're looking for new tools on how to attack them, please come and talk to me, and we can see if we can, if I can give you some information about some references or so that could be interesting for you to look at. But to start, let's start with some motivational problems. So I was motivated to enter the field of machine learning and to start studying this by my then PhD student, Robin Schneider, who thought that these were excellent tools to explore the string landscape. So a problem that has been driving the use of machine learning in string theory has been to try to build or study vacua of string theory from string compactifications that have certain properties and use machine learning as a tool to achieve such vacua. So to help in the calculations that you need to do, the computations, the analysis that you need to do, and will be the main focus of this talk. But one can also apply it elsewhere, so one could imagine using machine learning for the swampland program, so thinking about whether machine learning could help build, analyze, or classify UV complete effective field theories like the one we heard discussed yesterday in Irina's very nice talk. Machine learning has also been used to do numerical computations of interest for string theory, both in the setting of the conformal bootstrap and in the geometric setting that I'm interested in computing Ricci flat Calabi-Yau metrics. Machine learning can be used to learn mathematical structures, which may be of relevance for physics, and one can also turn the problem around and try to use physics and math to understand machine learning and why it works as well as it does. So there's progress of all of these topics, there's literature on all of these topics, and of course I cannot cover all in the 25 minutes that I have. So I will direct you to, in particular, this review by Fabian Rühle from a couple of years ago here. It's a physics report, it's quite long, and it has a lot of material, both describing the methods that people have been using and the kind of problems that they have been studying up to that time. So this is really a great introduction to the field. There are also some more topical reviews that are listed here, which go into more details, more specifics than Fabian's review. So why do we want to do machine learning? Well, the main reason is that it works. It can detect images of cats, and it can, now I'm going too far, and it can play games, and it does so it can beat humans at tasks that we would like to do, basically. So it may be that we want to play some complicated game like Go, or we may want to automate some task. We may want to label lots of images saying what's on them. We may want to have some translation from one language to another, and you can use machine learning for this. And these recent successes have been driven by a lot of different achievements in the field of machine learning. So there's better software, the neural networks that are designed today, their architecture is much more efficient, the optimizers are better, the hardware is better, there is more data and more money for training, And there are, if you want to get into this field, it's good to know that there are also very user-friendly libraries that you can use in order to study the kind of problems that you want to study. And at the core of most of these methods are neural networks, so some sort of algorithm that process some data that you feed into the system to give you some output at the end. And it does so by these kind of structures here, which are called neural networks. So in theoretical physics or in math, what can we do with these kind of tools? Well, first of all, we need some data, and a reason why people have started studying this in the field of string compactifications is that there we had data sets already available. So we had the huge data sets of Calabi-Yau manifolds that could be studied using machine learning tools. So by studying this data, machine learning can help us to find patterns, a bit like in the swampland. When you want to find a swampland conjecture, you want to study many, many examples and you want to find some pattern. You can do similar things with other kind of mathematical or physical data. Using these patterns, you can gain some intuition and make some conjectures. And then you can use that information to go on and study the problems and solve the problems that you want to study. And machine learning can also be a tool that we can use to speed up computations that we want to do. So in the setting then of the string landscape, where we want to build string vacua, here we need to do computations that are related to the topology and geometry of the extra dimensions, and these are often hard. Even if we have methods for doing them, it may not be that we can always practically perform the calculations that are needed to be done. So these are algorithmic computations that we do on the computers already, but they may just run out of memory or run out of resources, and then these standard methods fail. So we can try then to use machine learning as a way of bypassing that kind of problem. So how does this work? Well, a simple example, the first example that was explored in the string theory community, as far as I know, is to try to use supervised learning. So that's a technique of machine learning where you have your data set, which has some input. In the case here, it would be some images of cats and other animals. Then you translate these images into a pixel matrix. You feed this matrix, sorry, I'm really bad at pointing with this thing. You feed this matrix into a neural network, and then you train this network on a data set where you know both the input and the output, and by training, the network learns how to classify whether this is a cat or a dog or a cow or so, with some given covenants. So this is a prototypical example of machine learning. You do image classification via pixel matrix. And this is interesting for Calabi-Yau topology because Calabi-Yau manifolds are encoded as integer matrices as well. So we can take our Calabi-Yau manifold and we can encode it in its configuration matrix. So this is a CC, and you have an integer matrix of some sort. You may have Calabi-Yau constructed in some other way, and then the matrix will represent something else. But basically, it's a matrix with integers. And you can feed this into the same kind of machine learning tools that exist for image classifications, and you can predict the Hodge numbers of this manifold from the configuration matrix. And this is not magic in any way. I mean, we know that the topological information is there in the configuration matrix because it carries that information. We know how to compute these things using algebraic geometry. What happens here is that we bypass those routines that we would need to use and use these machine learning recognition methods instead. So you can reach very high precision by doing this. On the other hand, this might seem a bit uninteresting because we already know these Hodge numbers, so we might want to look into some problems that were not known instead. And this has been done. So using similar kind of techniques, you can go to look at other topological numbers associated with string compactifications and Calabi-Yau. So for example, I've studied vector bundles or line bundles over Calabi-Yau manifolds where we are interested in knowing their cohomology dimensions because that feeds into different kinds of physics models that uses these kind of constructions. And then with machine learning, several groups of people studied this using different kinds of tools, and this led to a detection of different, of a pattern where these Hodge numbers are described by some analytical formulae that can be learned then using machine learning. And these, this has some interesting structure here, where M0 and M1 here are the charges of a line bundle over a particular Calabi-Yau, and one can find these regions in this charge space where there are some simple polynomial describing what the Hodge number would be, what the cohomology dimension would be for this line bundle. And the same kind of techniques have been applied in other kinds of geometric settings. So that's topology. We can learn topology from machine learning, and we can use that to detect some patterns. Another thing that we might be interested in doing is to use machine learning for Calabi-Yau geometry. So Calabi-Yau manifolds are famously known to admit Ritchie-flat metrics, but also famously we do not know what the expression for that metric is. Excuse me. So we know from the Calabi-Yau theorem that such a metric should exist, and it's unique in any given Kähler class, but we do not have an expression for it. So the question then is whether we can use machine learning as a way of numerically computing this metric, and the answer is yes. So the idea then for this method is that there is certain information about these Calabi-Yau geometries, these Calabi-Yau metrics that we know. So we have access to a reference metric or a reference Kähler form of different types. So it's not hard to write down a metric on a Calabi-Yau manifold. What is hard is to write down the Ritchie-flat metric. So we can take some other reference metric that we know, and then we know by the Calabi-Yau theorem that the metric that we're after, which is Ritchie-flat, it will be related to this reference metric by an exact addition of an exact term, which can be written in this way, and phi here is a global function. So then we can translate the existence of this Ritchie-flat metric into solving this Monge-Ampere equation for the function phi. So this gives a second-order PDE for phi, which is hard. It's usually we're interested in six-dimensional spaces, or compact. So it's not easy to solve this, but it's better than just trying to impose the Ritchie-flatness condition on the metric directly. So what we can do then is that we can sample points on our Calabi-Yau, and we know how to do that now for basically any kind of Calabi-Yau. We can compute these reference forms. So J I already mentioned. Omega here is the holomorphic top form, which we can, given how we construct the Calabi-Yau, we know this information. And then we can solve the Monge-Ampere equation for phi numerically. And this is something that people have thought about before using machine learning. So there are methods from about 20 years ago now, where the first ones, where you numerically solve for these metrics using certain algorithms. So Donaldson proposed an algorithm for doing this, where you expand the function that you're after, phi, in a basis of functions, which are given as of polynomials on your Calabi-Yau. So there's some polynomial basis, and then the order of this polynomial will determine the accuracy of your numerical prediction, and then you can solve this problem order by order in this accuracy parameter, the order of the polynomial basis. So this has been explored using different kinds of techniques, some fixed point iteration scheme and some functional minimization. And it leads to very good predictions on very particular types of Calabi-Yaus. So the problem was it was solved, basically, but only for specific types of Calabi-Yaus. And these Calabi-Yaus, where this method worked, are the ones that have a high degree of symmetry, so that the basis that you expand in does not become too large. So you want to go to high order in K, but then the degree of K also is K also sets the degree of the polynomial, so you get very many polynomials if you go to high Ks. So machine learning methods then allow us to bypass this, and this is something that has been studied by a lot of people over the past 5 years. And the methods work more or less like this. So the idea is that you take your point sample, you've sampled the points on your Calabi-Yau, say 100,000 points. You also have the moduli of the Calabi-Yau, which determines what kind of geometry you actually have. And then you feed this as input into a neural network of this very simple form here. So it can be some simple neural network with maybe a bit wider than this one. Maybe you want some 100 nodes or some 60 nodes in your in every layer of your network, but you don't need a lot of layers. You don't need deep neural networks for this. You can work with quite shallow neural networks, and you can achieve the same performance as you have for this fixed point iteration scheme by training these kind of networks for about half an hour or even 10 minutes on your personal computer or your laptop. Whereas with these numerical methods as we had before, you really had to use much more computational resources to work even on these simple manifolds, and going to more complicated Calabi-Yaus was just out of the question. So because of the simplicity of these networks here, or maybe because of that, we don't really know why it works so well, this kind of method works for many different kinds of Calabi-Yaus. And what this network does is that it outputs the Calabi-Yau Kähler-form and the Calabi-Yau metric for you. So the metric is really encoded in this neural network. So the neural network is your approximative richly flat Calabi-Yau metric. And how does this work then? Well, you set up your network and then you encode the constraints that this metric should satisfy, for example, Ricci flatness, or being globally defined, or being Kähler, depending on how you set up the problem. And then you train the network using the standard routines of machine learning, and you check performance afterwards. So you have some error measures that you check on some test data sets. So you have your training set of data, and then you have some unexplored points in your Calabi-Yau where you check whether things work or not. So there's a lot of work also ongoing on this, and there's work on improving the accuracy and performance of this, including moduli dependence is something that people are very interested in, particular complex structure moduli dependence. Kähler is a bit more hard, I can explain why. And then, of course, using these for physics and math is something that has been starting to appear in the literature in the past year and in this year. Okay, so these were two ways of using machine learning in string theory, and it's a kind of, finding new ways of performing computations that we already knew how to do. So in the last 5 minutes or so that I have, I will go into talking about search tools that we get from machine learning. So if we want to search the string landscape for nice vacua, what kind of methods are they? And there are a couple of methods. I will focus on one of them, which is known as reinforcement learning. So reinforcement learning is the technique that was behind machine learning beating the world champion of Go a couple of years back. The idea of reinforcement learning is that you have, there are neural networks in the game, but they are not really visible. So you have an agent here, and the agent is observing an environment. It could be the Go board or some other environment. The agent is in a state in the environment, so it has some configuration on the Go board, and then it will take an action, so it will swip some pieces. Actually, I don't know how you play Go, so it will do something with these black and white marbles. I don't really know. And then it will get into a new state, and if that is a good state, it will get a positive reward, and if it's a bad state, it will get a negative reward. And it will learn from doing this many, many times what are the good things to do. So the idea then is that you train the network to learn how to win this game or to solve the environment by receiving rewards. And this has proven to work well in large environments and also with imperfect information. And these are two things that we need to deal with in the string theory landscape. So we don't know everything about the string theory landscape, and we also don't expect to be able to explore it completely because it's so large. Now, importantly, in this method, there is no approximation. So the two methods that I talked about before, there you have some, you make a prediction with some circuit accuracy. There's an uncertainty there. Or with the Calabi-Yau metrics that you compute, that's a numerical approximation. There's an error in there. But here in reinforcement learning, you don't really approximate anything. You just look for new solutions. And you train the network, or you train your agent to find these solutions. And the way that you do that is that the agent will take decisions based on a policy, and that policy will be a neural network. That is the thing that you train. So you get really exact solutions from this, and you can also discover new strategies for how to do things, how to search for how to solve, how to win games, and how to search for new string vacua. So then, if you want to use this method in string theory, then you need to think about, okay, what kind of problems can I turn into a game of this sort, where I know the environment, I know the kind of actions that I can take, and I know I can set up a reward structure for how this should work. And this has been used in different kinds of string compactification. So in the first paper on this was intersecting brain models in 2019, and then it has been used for heterodic standard models, type-cubic flux vacua, conformal bootstrap, and also knot theory, maybe not really string theory, but it kind of fits here because of the people who have done it. And the idea then is that you have this agent who is absorbing this environment, which will then be the string theory setup or the physics setup that you're interested in, and you set up some states, or you know the states of this. So the state in a string theory compactification setting would be, okay, what kind of Calabi-Yau manifold do I have? What kind of vector bundle over that Calabi-Yau manifold do I have? And then the reward would be based on whether this configuration satisfies, giving a particle physics model with 3 matter generations, for example, or the gauge group of the standard model. So this is one method for doing this, reinforcement learning, and there are other methods. One is known as genetic algorithms. I will not describe it, but you can see in some of these papers that they compare with that method, and they have different characteristics and different pros and cons, so it's good to be aware of both. Okay, so here are some experiments that I did with my PhD student Robin, and what I wanted to show in this slide is not so much that we could plot things, but rather that we could explore different kinds of actions in this environment that we were studying, and the strategies so these correspond to different strategies that you take for exploring your string landscape. They are outperforming random walkers, both of these strategies. This one here, which is different from a systematic scan, so very different from what you would imagine doing as a human, is really, really good at outperforming the random walker. So it gives you some new way of thinking with the problem, how you should work with it. And also because with reinforcement learning, you need not systematically explore all vacua of your string landscape. You can just go for the interesting ones. This means that you can reduce the time that you spend on computing things, and this means that you can go to regions of parameter space that were not explorable before. Okay, so let me wrap up. To conclude, I hope I have convinced you that yes, machine learning methods can help string theory. We can bypass hard computations, we can detect new patterns, and we can improve numerical approximations using these methods. So if you want to use this yourself, I would also like to give you this little roadmap here. So I think I'll just leave this for you to read and say thank you for listening.
Questions?
Thanks. This is a question about new patterns. Can you give an example of some type of new unexpected patterns that were noticed thanks to machine learning? Well, question, do there exist new patterns that were noticed thanks to machine learning? And what are they?
Yes, there are. So this pattern with the line bundle cohomologies, it was expected. So that was not completely new. It had been observed in some examples, and with machine learning, one could see it more broadly. There have been patterns observed that go beyond our field. So, to be honest, I'm not sure I could pinpoint some discovery in string theory that has come from machine learning yet. But there was a famous paper from last year in knot theory where they managed to detect some patterns about that led to a theorem, some inequality that could actually be proven, and that was not known before. So it was a relation between different invariants, algebraic and geometric invariants of knots, and that relation was not known before. So it has helped, but it's really, it's not like you just, feed some data to the algorithm and then it spits out something at you. You really need to work with the data and you need to analyze and try to really condense the information that you get. So if you have some neural network that has been trained and that predicts something, then maybe you want to do some pruning of that neural network to see if you can cut away some things and get some clearer patterns that you can then analyze and make some conjecture from.
Other questions?
Thank you for your talk. So you've mentioned the connection to string theory. What about some other problems, such as, I don't know, scattering, particle physics, and so on? How much has this been explored?
It has not been explored that much, but I know that people are thinking about it. So I expect that there will be publications.
Thank you.
Any other questions? Yes.
I was wondering, can you use this to try and find beyond Calabi-Yau compactifications,
yes,
or like back-reacted flux?
Yes, you can. Some of these Calabi-Yau metric networks, the ones that I've been working on, they are designed in such a way that you can generalize them to go beyond Calabi-Yaus. And this is work in progress, really. So no one has. There's actually one paper where they find Strominger-Hull solutions using the same methods. But beyond that, it hasn't really been explored. But I think it should.
Thanks.
Anyone else? Okay, let's thank the speaker again for the nice talk.